All right. Now we are moving on to the first long talk by an abstract submission. And this presentation is going to be delivered by Lisa Handl from University of Tübingen. It's actually a proceedings presentation entitled Weighted Elastic Net for Unsupervised Domain Adaptation with Applications to Age Prediction from DNA Methylation Data. And the presentation should appear on the screen, but it does not. Oh yeah, this looks good. Okay, thanks.
Thank you very much. I'm very happy to be here, and I also want to thank the organizers for giving me the opportunity to present some of our work to you. Is there a pointer? Yeah. Okay. So at the core of the problem that we consider is heterogeneity in real-world data. Usually, whenever we apply machine learning algorithms, we're making one very central assumption. That is, that the training data comes from the same joint probability distribution as the data on which a model is later applied. And if this is the case, we can take the training data, fit our model, and if we predict for new data from the same distributions, we will be close to the truth. However, in the real world, this assumption is often violated. And if our new data has a distribution mismatch with the training data, even if it's just a simple shift, as in this example, our predictions can easily be far from the truth. And there are many reasons why this may happen in computational biology. For example, we have seen one in the keynote with data from different hospitals. New data might be measured with different devices or protocols. Batch effects, unknown or uncontrolled confounders can cause these problems. And it might even happen intentionally if we want to transfer knowledge between different but related domains. Unsupervised domain adaptation tries to deal with this situation, and it specifically tries to learn from a well-studied source domain with lots of available data to predict on a less studied target domain, where the data in source and target domain have slightly different underlying distributions. In particular, unsupervised domain adaptation tries to do this using only unlabeled examples from the target domain for training. Unsupervised domain adaptation is well studied in computer vision, for example, for classification problems like object recognition. And here, distribution mismatches can arise, for example, because images of the same object can be taken in different contexts. Like in this example, you can see some monitor images from Amazon or from office environments, which obviously look different. And here, mainly deep neural network-based methods have been used successfully. Unsupervised domain adaptation is less studied for regression problems and for settings where the number of variables is much larger than the number of samples. Unfortunately, especially these settings are relevant in computational biology. A popular standard model for this scenario is the elastic net, which is a regularized linear regression model that combines advantages of ridge regression and the lasso. And what we propose is a method for unsupervised domain adaptation that is suited for this scenario and based on an elastic net. We call our method WENDA, which is short for Weighted Elastic Net for Unsupervised Domain Adaptation, and it deals with the following situation. We have a number of labeled examples from the source domain distribution, where x1 to x5 are inputs and y is the output, and a number of unlabeled examples from a different but related target domain distribution. And our goal is to use the source domain examples and target domain inputs to make predictions for the unknown target domain output. And our main idea to achieve this is to compare the dependency structure between inputs in the source and target domain. Usually, in biological data sets, variables are not independent, but do have characteristic dependencies. And if we can detect differences in these dependencies between source and target domain, like for x4 and x5 in this example, it might indicate that they also have a different relationship with the output y. So what we do when training a model is we enforce a stronger regularization on these variables where we detected differences and force the model to rely more on the remaining variables that behave similar. And if we trained our model, we can use it to make predictions for the output and the target domain. More formally, domain adaptation deals with two different but related joint distributions, PS and PT over X and Y, which can both be factorized into the conditional distribution of Y given X and the marginal distribution of X. And one classical assumption in domain adaptation is that the difference between these distributions lies only in the marginal distribution of X, and that the conditional distributions of Y given X are actually the same in both domains. What we do is we weaken this assumption by assuming that the conditional distribution of Y is the same given only a subset Xm of all features. And we additionally assume that we can find such a subset by looking for variables which have the same conditional distribution given all remaining variables in the two domains. I'm writing approximately here because we are not strictly testing this and including or excluding variables. Instead, we are proposing a quantitative measure for how similar these dependencies are and introduce a feature weighting. So what Wenda does to compare dependency structures is it trains a model for every single feature that predicts this feature based on all remaining features. Here we use Gaussian process models with a linear kernel, which is basically a Bayesian version of ridge regression. And the advantage of having a Bayesian model in this step is that we don't get just a single predicted value, but a posterior distribution that includes uncertainty information. And all these models are trained on the training data, so they capture the dependencies between inputs in the source domain. And what we can do next is we can compare this learned dependency structure to what we see in the target domain. For every target domain input and feature, we can look at the actual value we're seeing and compare it to the predicted distribution that we get when we plug the remaining features into the corresponding feature model. And we compute this confidence score, which is from the paper by Jalali et al. And it's basically the blue area here and a two-tailed p-value, so it's large when the actual value is near the center of the predicted distribution and small otherwise. We average these scores over all available target domain inputs to get one confidence score per feature that tells us how well these learned source domain dependencies of this feature still fit in the target domain. In the end, we train one final model using these confidence scores to predict the output we're interested in. Here we use a weighted elastic net, which solves this problem. Like a standard elastic net, it tries to minimize the residual sum of squares of the training data, plus a penalty term. And the penalty is a combination of the L1 norm and the L2 norm of the coefficients of all features in the model. The only difference is that the contribution of each feature is scaled by an additional feature weight. And in our application, we set those feature weights to 1 minus the confidence I introduced before to the power of k, where k is a user-specified parameter. And this has the effect that features with low confidences contribute more to the penalty, and their coefficients are driven to 0 more quickly than those of high confidence features. And since our model still tries to achieve a low residual sum of squares on the training data, it automatically tries to compromise between a low training error and a good feature set in terms of high confidences. We applied our method to the problem of age prediction from DNA methylation data. DNA methylation is a well-studied epigenetic modification where a methyl group is added to cytosins, mainly in CpG sites. And it is known to play an important role in many gene regulatory processes, but is also known to change characteristically with age. And therefore, multiple authors have trained models to try to predict age from DNA methylation data. For example, Steve Horvath did so using an elastic net model. And they usually try to fit the chronological age of the donors as closely as possible, but interpret the output of the model as a biological epigenetic age. And differences between the chronological and the epigenetic age could be linked to lifestyle and disease history. DNA methylation patterns are also known to be tissue-specific, so predicting age from other tissues than were available for training is a domain adaptation problem. We consider a data set of healthy tissue samples from GEO and TCGA, where DNA methylation was measured with an Illumina 450K chip. And for computational reasons, since we have to train all these feature models, we reduced the initial number of features to roughly 13,000 using a standard elastic net. And our final training set consists of more than 1,800 samples from 19 different tissues with a focus on blood. and our test set of roughly 1,000 samples from 10 tissues. The test set also contained some blood samples, but additionally contained tissues that were not part of the training data, for example, the cerebellum. In our setup, we keep the training set fixed, but consider each tissue in the test set as a separate target domain. If we want to apply Wenda to this problem, we have to make several choices for parameters. The first parameter is the proportion alpha of L1 and L2 norm in the penalty. This we keep fixed at 0.8 as a design choice. The second parameter is the strength of regularization lambda. Here we explore two main paths that lead to different versions of our method. For the first one, Wenda CV, we use cross-validation on the training data to determine lambda. This is what's usually done for a standard elastic net, but it can be problematic in a domain adaptation setting because it will try to find a value that's approximately optimal for the source domain rather than the target domain. As an alternative, we try to exploit prior knowledge on the size of the domain mismatch to choose a good value for lambda. The idea behind this is that in Wenda, lambda is not only the strength of regularization, but it's also related to the strength of adaptation. Because if lambda is high, the penalty has a lot of importance, and then also the feature weights have a lot of control over the final result that we get from the model. So what we do is we use published tissue similarities from the GTEx consortium, and you can see a cutout of the original figure on the right. And we mapped their tissues to our data and used the tissue similarity as a proxy to select a good value of lambda. The last parameter of our method is the weighting parameter K. This was newly introduced by our method, and we evaluated sensitivity empirically. We first applied a standard model to our dataset. This is the model type proposed by Horvath. It's a standard elastic net followed by a linear least squares fit to only those features that received a non-zero weight in the elastic net. And what you can see is the predicted age versus the true age for all test samples colored by tissue. And it performs already quite good for most tissues, with one exception. All these samples here are from the cerebellum, and for those, the predicted age is always far below the true chronological age. So these cerebellum samples are hard to predict for two reasons. First, they were not part of the training data. And second, the cerebellum is known to be biologically different even from other brain tissues. So these are samples that obviously have a distribution mismatch with the training data, and we want to focus our evaluation on whether we can improve predictions on these samples. Here you can see a comparison of the mean absolute error of the standard method and different versions of our method. First for cerebellum samples on top, and on the bottom for the full test set. So the versions of our method we're comparing are Wenda PN using prior knowledge, Wenda CV using cross-validation to choose lambda, and Wenda MAR is an additional second baseline where we use a simpler feature weighting that is based on the marginal distribution of features rather than the dependencies between them. And what you can see is that Wenda PN and Wenda CV clearly outperform the reference on cerebellum samples, getting much lower mean absolute test error, and that Wenda MAR is also far better than the reference, but not quite as good as our method. And on the full test set, you can see that we're overall in a similar range. We're a bit better for some parameter selection and a bit worse for others, but the differences are not as dramatic as for cerebellum samples. On the next slide, I'm going to show you a comparison of the predictions of the standard model and one version of our method. And I'm choosing Wenda PN with k equals to 3, which is one version that performed very well, but not the cherry-picked very best version. So here's again the predicted age versus the true age for the reference model on the left and for our method on the right. And as you can see, the predictions got slightly better for most tissues, but more importantly, all these outliers here are gone now, and we actually predict almost as well for cerebellum samples as for the remaining ones. So in summary, I've told you about Wenda, our method for unsupervised domain adaptation based on an elastic net. It makes use of dependencies between the inputs and weights features according to how similar they behave in the source and target domain. We've evaluated our method on DNA methylation data on the problem of age prediction across tissues, and we could show that we achieve far lower errors on cerebellum samples than a standard model, even though labeled examples from cerebellum were not part of the training data. So we could show that at least on this kind of data, our method is able to predict on new samples, even if they have some distribution mismatch with the training data. We additionally validated our method on simulated data. I did not have time to tell you about this in the talk, but you can find it in the proceedings paper if you're interested. And source code for our method is also available on GitHub. So thank you very much for your attention. And I also want to thank my supervisor, Nico Pfeiffer, everybody from our group and everybody I worked with, and our source of funding. I'd be happy to take questions.
So I have a question for you. Very nice talk. In order to build a Wenda model, it seems like you need data then in 2 domains so that you have a target domain to test in. So in the context of looking at different cell types, you wanted to predict in the cerebellum, but that was not used by the Wenda model.
Exactly.
Okay.
So we're using the, if we want to predict for cerebellum samples, we have some inputs for cerebellum samples for which we want to know the output. And what we do is we compare these inputs to the inputs in our training set, but we don't use labeled examples from cerebellum.
Okay. And so if you were to train a Wenda model, would it be possible to, I don't know, learn features in 2 tissues, but then do you think it would have value in the 3rd tissue even if it was a totally new domain?
If we can first do our comparison of the inputs and the dependency structure between them, I think that would work, yes. Okay. So there's one expensive step in Wenda that is training all these feature models. And this we have to do once for one fixed training data set. But once we have the feature model, we can predict on multiple target domains and just compare those trained feature models to different target domains, so to different samples from different tissues, and predict for these specifically.
Thank you.
Thank you.
Hi, so this was a really interesting talk. So we have also come across a similar type of problem in a slightly different domain. So one question that came up to my mind is, I mean, obviously you showed that this particular approach works in the context of an elastic net, right? So, but now imagine so that you would like to apply this to, let's say, a nonlinear model even with other type of data. So would this be possible, or could you imagine a certain extension of your approach in this direction?
I hope so. So we would definitely be interested in trying that. And I think it should be relatively straightforward to extend it to nonlinear regularized models, because the main idea is to use those confidences to increase regularization on some features that we think should not be used for this domain transfer. And I would hope that if we use a nonlinear model, that we could also do this, but we haven't tried it yet.
Okay, thank you.
Thank you very much.
Yes, very nice talk. So here, so my question is that would you suggest, in case you have a data set, under what conditions you will recommend your method over the traditional elastic net? So what is the best cases for the applications?
So I would recommend it when you do expect that there is a distribution mismatch. So if you know that your test data does have a somewhat different distribution from the training data. And also, I mean, our main assumption is that the dependencies between features are useful for figuring out which features are problematic for domain transfer. So if you think features in your data set do have characteristic dependencies and that they could help you decide which features you want to use, then I think you should use Wenda.
Thanks again for all the questions. And thanks also to the speaker for a great presentation. Let's thank her again.